Hello and welcome to my talk about MineSweeper, a low overhead way to prevent use-after-free vulnerabilities from being exploited without breaking compatibility with pre-existing, pre-compiled programs. In this talk, I will start with a high-level overview of the threat, show the attack, propose a solution, talk about how we can make the scheme concurrent, introduce some more optimizations, and wrap up with some results. We consider a non-malicious application running in the presence of an attacker. The attacker has powers to allocate objects and use the objects that they have allocated. That means writing to them and reading the contents. Their goal is to perform privilege escalation. You can think about this as a web browser running a script from a malicious website which is trying to break the sandboxing mechanism. A memory allocator obtains memory from the operating system using system calls, for example, SBRK or mmap. When the application calls malloc, the allocation is returned. At this point, references can be made to the allocation, and those references can be used to access the object. When the application thinks that it's done with the object, no more accesses will be made, then it calls free. At this point, there might still be some references which are now dangling. These in and of themselves are not a problem. However, we cannot make accesses through them. In particular, if a future malloc call returns the same object, then we might end up in a situation where we have old dangling references and new non-dangling references. Accesses made through the non-dangling references are valid accesses, so no problems there. But accesses through the dangling references target the old object, but access the contents of the new object, and this is a problem. MineSweeper breaks this loop by introducing a third quarantine state. Objects that are freed by the programmer end up in quarantine until an automatically triggered linear sweep of memory proves the absence of dangling pointers. When there are no more dangling pointers, there is no way to address the object, and therefore there is no way to trigger a use-after-free after this point. There are a few things to note about this. Firstly, note that our scheme is semantically safe. We require the programmer to explicitly free every allocation that we deallocate. This is unlike garbage collection in low-level languages. Also note that we do not prevent use-after-frees from occurring. Objects in the quarantine can still be accessed even though they've been freed by the programmer. However, we do prevent use-after-reallocate, which prevents all aliasing, and therefore it prevents exploits from working. Also note that this is a non-probabilistic scheme. We provide specific guarantees, and we will keep allocations in the quarantine for as long as it takes to provide these. We can amortize our work away by only sweeping once the quarantine size has reached a certain threshold. We do not sweep on every free. Instead, we wait until the quarantine has reached 15% of the overall memory size, although this can be tuned. Let's look at the base version of this algorithm. The program is running, and on every call to free, it inserts a new allocation into the quarantine. Once the threshold is reached, we stop the world and perform a sweep. This can be done in the same thread for now. The sweep consists of two phases, a marking phase and a deallocation phase. In the marking phase, we look through all of memory and registers and mark the target of anything that could be a pointer. In the deallocation phase, we check the marks and deallocate objects that are unmarked. After this, the program is resumed. For this, we use two main data structures. The first one is a shadow map. Conceptually, this is a flat array of bits corresponding to the heap. It is mapped on demand, and it contains one bit for each 16-byte granule of memory. This means that our virtual memory overhead is less than 2%, and our physical memory overhead is much smaller. This bit will be set if we found something that could be a pointer to that granule. The second data structure is a quarantine, which is just a list of allocations where we append every freed allocation. So let's look at the algorithm. in more detail in a pseudocode. We go through, in the marking phase, we go through each word of memory and make a mark in the shadow space for the target of that word, interpreted as a pointer. Of course, the word of memory might not be actually a pointer. It could be just an integer or a couple of bytes of other data like text, but this doesn't really matter because a random piece of data pointing to an allocation is very unlikely because of the vastness of virtual memory space. And even if it does, we just delay the deallocation by a little bit on that one allocation. In the second phase, we walk the quarantine list. For each allocation, we check if any of the granules of that allocation were targeted by pointers, or they're marked in the shadow space. If none of them are marked, then we can release the allocation. Otherwise, we will keep it in quarantine. Finally, we will clear the shadow space so that it doesn't take up space and it can be reused for the next sweep. So this is the sequential version, but we can try to parallelize it. But before we do, let's look at some security guarantees that our scheme provides. This scheme provides a guarantee that allocations are released only if there are no pointers to them left anywhere at the point of time when the sweep is performed. In the sweep, we check all of the memory, including the heap and stack, and we can also check register contents. We can make this scheme more efficient by making it concurrent. When the sweep is triggered, we continue running the application while the sweep is proceeding in the background. At the start, we reset page table dirty bits. Therefore, once the sweep has finished, we will know which pages have been changed. At this point, we stop the weld and re-examine only those pages that have been written to. We also save the quarantine so that once this re-sweep is done, we can restart running the program with a fresh quarantine. Deallocation can happen in the background on the old quarantine, and anything that we didn't deallocate will be re-added onto the new quarantine. This provides the exact same guarantees as the sequential version, except we moved the point of time where we check logically to this re-sweep. We can make the scheme even more concurrent by never stopping the program and doing away with the stop the weld phase. In order to provide a reasonable level of guarantees, we save the quarantine at the start of the sweep, and we will only deallocate objects from this old quarantine. This means that we are able to provide the same level of guarantees as before for programs that do not move around their dangling pointers. In particular, for any allocation for which the dangling pointers cannot be moved around, we will provide the exact same guarantees. A little change is that we only sweep memory here, because register-based use-after-freeze should be easy to debug using static analysis, and the time it takes to do the sweep should be enough to overwrite any register contents anyway. Another optimization we performed was zero filling. This is very important. When an allocation enters the quarantine, we zero fill its contents to wipe any dangling pointers it could possibly contain. This allows us to free chains of objects that reference each other in a single sweep. Without zero filling, this chain would take multiple sweeping rounds to free because we cannot free the second one until the first one has been wiped. After zero filling, we can free all of these allocations, including ones with circular references. Another important optimization is unmapping physical pages backing large allocations. Large allocations are allocations that have multiple full pages of memory. We can unmap the physical page backing the virtual allocation. This transforms our overheads from physical memory to purely virtual memory. Doing so reduces the resident set size impact of the quarantine and therefore lets us perform fewer sweeps, because we can exclude these allocations from the threshold. We still have a secondary threshold for conserving virtual memory overhead, but this can be much larger because of the vastness of virtual memory space. There's now a danger, however. When the sweep is triggered, it will scan through memory, and the operating system will remap the physical pages on demand when we read from these pages. That means we must exclude these from the sweep. Doing so, however, introduces a blind spot in the sweep. Pointers could be dumped onto these pages. We prevent this by removing permissions from these pages and locking them. This means that this page cannot get remapped, and it will never have pointers because its contents are just 0. We must now also prevent access during the sweep to these pages in order to prevent segfaults. We can restore these permissions when the allocation leaves quarantine, thus remaining completely transparent to the allocator. Another optimization using a similar method but for a different purpose is fragmentation management. jmalloc, like most memory allocators, performs some sort of cleanup when the composition of allocations needed in terms of size changes. jmalloc will use a sigmoidal decay function to walk its free lists once roughly every 10 seconds. In the free list walk, it will call purge on any pages that no longer have any allocations on them. Demand paging will be used to remap these pages when needed. Of course, this suffers from the same issue as before with MineSweeper. A sweep would just touch these pages and remap them. Because of this, we hook onto the decommit and commit hooks of jmalloc. Therefore, we will have a callback on both when purging would have normally occurred and when the page is needed the next time. We use the same mechanism as for quarantine unmapping. We lock the page and we remove the physical page backing it and prevent the sweep from touching the page. Let's look at some results. MineSweeper achieves a runtime overhead of just 5.2% and a memory overhead of just over 12%. This is significantly better than previous schemes in literature. Marcus is worse both in terms of memory and runtime. ffmalloc slightly outperforms us in terms of runtime, but its memory overhead is significantly worse. Note the logarithmic scale on these axes. This is even more apparent when we look at the worst case behavior. Note that ffmalloc's overhead is over 10 times, whereas MineSweeper's is 1.7 times. Thank you for listening to my talk, and please read the full paper, which contains a lot of interesting discussion around more optimizations and some more formal definitions, for example, around the threat model. If you have any questions, don't hesitate to email us, and we will be very happy to answer them. Thank you.